Hi, welcome to Chapter 12, Solids and Modern Materials, Part 1. We're going to talk about how to classify solids, the structure of solids, and metallic solids. So how do we classify solids based on bonds? Well, there's four types of bonds that you could have. There's the metallic solids that are held together by a sea of electrons. There's the ionic solid that is the attraction between the cations and anions that are mutually attracted to each other. And that's what you see here, okay? Then there's covalent network solids, which are joined by an extensive network of covalent bonds, and that's this picture right here. So it's covalent compounds that form a crystal structure. And then there are molecular solids that are discrete molecules held together by weak intermolecular forces. So when we think of covalent bonding, this is normally what we're thinking about. One organization of solids is either to call them crystals, which means they have a repeating pattern. You see here, there's a repeating pattern going on in all of these. And since crystal and solids have a regular pattern, they are of most interest to chemists. Okay, you have a highly ordered arrangement. Then you have your amorphous solid, which has a lack of order. It's more random. And that's what you see here. See, this is more random in here. There's no particular order in the arrangement of the particles. So an example of this would be glass. Example of a crystal would be quartz. And believe it or not, they both have the same chemical composition. See here, SiO2 and SiO2. If we're looking at our crystal solids, we have something called a unit cell. It is the smallest repeatable pattern within the crystal. So its repeatable pattern is the unit cell. So here are 7 different types of unit cells that you could have. The structure of the crystalline solid is defined by the size and the shape of the unit cell and where the atoms are located within the unit cell. The geometric pattern on which the unit cell is based is called your crystal lattice. And in 3 dimensions, there are 7 basic crystal lattice that can describe all crystals. And you have cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. And here is these A, B, and C's are your lengths, where this is A, this is B, and this is C. And alpha, beta, and gamma are the angles between them. Let's talk about your metals, or the metallic structures. So you could have what's called a primitive lattice, where you only have atoms at the lattice points. So here you see you only have atoms at the points. This is called a primitive cubic lattice. Then you could have centered lattice, where you have atoms in other regions, not just located at the lattice points. The most commonly is called body-centered or face-centered. These are 2 common ones. So here's your body-centered one. You still have your atoms at the corners, but then you have one atom right smack in the middle. This is called body-centered. Then you have face-centered, where you still have the atoms at the corners, but then on every face of the cube, there is an atom. So this is called face-centered cubic. This is called body-centered cubic. The structures of many metals conform to one of the cubic units. So simple cubic, body-centered cubic, or face-centered cubic. So here are some examples where they're showing the atoms a little bit larger. How do your atoms pack together? So there's something called closed packing. So in nature, it does not like empty space. It wants its atoms to be as close as possible. So the atoms in a crystal like to pack as close as they can. Two common packing shapes or types is cubic closed packing and hexagonal closed packing. So here's hexagonal closed packing, and you can see up here you have this alternating pattern, A, B, where the B atoms are sitting kind of in the divots created by the A patterns. Okay, and then you have cubic closed packing, where instead of just having an A and a B, you have an A, B, and a C. Okay, hexagonal packs closer than closed pack than cubic. So this will make a more dense packing. So let's talk about metallic bonding. We always say it's a sea of electrons, but what does that really mean? So you have your positive nucleus and core electrons are kind of in these circles. Then your valence electrons are kind of dispersed throughout. They are free to move. They are mobile. They are not stuck to one of the cores. They are free to move, okay? So metals are not covalently bonded, but there is an attraction between that. The attraction between the two atoms is stronger than van der Waals. So in metals, your valence electrons are delocalized. So they're not attached to one specific core. They can move around. So when you think of a metal, think of it as a group of cations suspended in a sea of electrons. This is known as the Electron C Model. The electrical and thermal conductivity, ductility, malleability of metals is all explained by this model. If you apply a current, these free electrons are going to start to move from the negative to the positive side. If you heat it up, again, you're going to be able to conduct the heat across the way. If you smack it with a hammer, this will allow some flexibility so it will flatten. So that's what malleability is. So here's another picture of your Electron C model. So here you have your positive core with these negative electrons that are free to move around. This explains many properties of the metal, like conductivity, heat, and electricity, and the fact that you could deform the metal without it cracking or breaking. What happens when you contain more than one type of metal? Okay, so alloys are materials that contain more than one element and have the characteristic properties of a metal. They don't necessarily both have to be metals, but that when you mix them together, they behave like a metal. So alloys are mixtures of elements that have properties that are characteristic of metals. And it's an important means employed to change the properties of certain metals. Say you have a metal and you have an application and it's not hard enough. Well, you could add another element to it to make a mixture that will have that will be harder, okay? So many of the ordinary uses of metals involve alloys. So here are a bunch of common alloys. Stainless steel is a good example. It's iron that has a little bit of carbon, a little bit of chromium, and a little bit of nickel. And once you do that, it doesn't rust, where regular iron would rust. So it resists corrosion. So a lot of your forks and knives, because you're constantly washing them, are stainless steel. I'm trying to think. Sterling silver is another good example. If you have jewelry that's pure silver, it will tarnish. For sterling silver, they add a little bit of copper to the silver, and then it doesn't tarnish. Bronze. Bronze is copper and tin mixed together. And brass, you have copper and zinc mixed together. There is more than one type of alloy. So we have our substitutional alloy, where in our substitutional alloy, the second element takes the place of the metal atom. And they both are around the same size. So you see here, you have gold, and you have some silver substituted in there. It's taking the place of the gold atoms. Then you have interstitial alloys, where the second element will fill a space in the lattice. So in between these, they're putting a little bit of carbon. Carbon is tiny, so it can kind of squeeze in between there. That's an interstitial alloy. Then you have heterogeneous alloys, where the components are not dispensed dispersed uniformly. And that's what this picture is showing. See the different structures within? So components of an alloy are dispensed uniformly. In a substitutional alloy, the solution particle takes place of the solvent metal atom. So because they are considered solutions, you have a solvent and a solute, but both of them are solids in this case. Okay, in this particular case, both of them are close in size, similar in size. And here's a picture of it. See, the yellow one is your substitutional element that's taking the place of the blue one. In an interstitial, the solute particle finds their way into the holes between the metal atoms. So here, see, it's in the holes and it's much smaller. This is called interstitial. An intermetallic compound is a compound, not a mixture. This, when you have the two different, in this case, elements, you will have a distinct property, okay, and a definite composition since they are compounds. It is ordered rather than being randomly distributed. Oftentimes, this is more brittle than the substitutional alloy. So this is not really an alloy, this is a new compound. And that is the end of part 1.